Hey guys, how's it going? This video is going to be about the p-value approach. Last time we did the critical value approach, but I wanted to show you something I just discovered. Check this out. Whoa, whoa. Null hypothesis, alternative hypothesis. Null hypothesis, alternative hypothesis. Oh, which side is the pink cowboy hat on, bro? Okay, we'll stop. I'll stop and go to the notes. So as you'll notice, these are pretty much the same notes we started with last time because the p-value approach and the critical value approach are pretty similar. All it comes down to is the comparison we make when we do our conclusion. So let's just go through the steps we've gone through for any hypothesis test so far. The first thing we do is a research question. So we went over these a couple videos ago, same research questions. Then we set up the null and alternative hypotheses right here. So just as a reminder, this question is the true average return of Amazon stock greater than 5% per year? If the answer to that is no, then the null hypothesis will be true. So HO, our null hypothesis right here, is mu is less than or equal to 5%, because that would mean the true average Amazon returns are less or equal to 5%, and the answer would be no. On the other hand, the alternative hypothesis is true if the answer is yes. So we have mu, the true average Amazon return is greater than 5% for the alternative hypothesis. And our whole goal to answer the research question is to decide which one of those hypotheses is true using statistics. So last time we collected our data and we collected some statistics based on that data, and that's what we'll do every time. I'm going to do that in Excel today so you can see how to actually implement this. One thing we chose and we introduced last time, at least in terms of hypothesis testing, is alpha, or the level of significance right here. So that's going to be 5%. That's a pretty common significance level, 0.05. Same idea as doing a 95% confidence interval, actually. So that's alpha right there, 0.05. But another common value is 10% or 0.1 and 1%, 0.01. You really choose that based on how safe you want to be. So for example, if you're trying to test whether a drug cures a disease, but that drug has like bad side effects, you might want to use a lower level of significance, which implies a higher level of confidence in your answer, so that you don't accidentally end up giving a bunch of people a drug with a really high, that doesn't actually end up working, but has bad side effects or something. So really what alpha you choose is totally up to the analyst or you. And you want to think about the consequences of a bad decision or a wrong decision when doing that. So if it's a high consequence decision, you usually want to lower. If it's like, well, I don't really care, then you can use higher. All right, so last time I'm going to use the same data for this part. We went and collected data on Amazon stock returns. This is made up data, obviously. And we got X bar equals 7%. We assume here that we know the population standard deviation is 10%. That means we're going to use a Z to get our conclusion. We have a sample size of 100. And then those two things allow us to calculate the standard error right there, right? Sigma divided by the square root of n. And that's just 1 in this case. Then with that information, we can calculate our Z statistic. 7 minus 5 is 2. Divided by that standard error right there, which we already calculated to be 1. 2 divided by 1 is just 2. So last time, in the critical value approach, we said, hey, this critical value, 1.65, is less than 2. And that led us to reject the null hypothesis. We got this 1.65 from looking at a Z table. So we said, hey, where is the 0.95 to the left? Because that would imply 5% to the right. It is right about there. If we go over and figure out the z value for that, we get 1.6. What's the number in the column? 0.05. So if we put those together, we get 1.65. The other way to do that, z critical value is the better way in Excel equals inverse, norm dot inverse 0.95, because it's looking for the area to the left. 5%, the alpha is to the right in this case because we're doing an upper tail test, comma 0, mean of a z distribution, 1, standard deviation of a z distribution, and I don't think we need true for this one. So we just give that, and that would have also given about 1.65. But that was the critical value approach, right? So notice another thing that I could do to get the p-value approach is I could say, well, what is the area? So I know 2 is farther away from 0 than 1.65, right? That's 2 right there. That's farther away from 0 than 1.65. So I know that line where 2 is on this axis is farther out. In fact, that's why I reject the null hypothesis. That 2 being black line being farther than the red line right here, this line being farther out than this line, is what leads me to land in the rejection region and reject the null hypothesis. Well, another thing I could do, notice that there's an area to the right of that 2, and that reflects a probability. This area right here, to the right of this 2, that area is called the p-value. All right? So I could, notice, instead compare the p-value. A p-value is a probability, which is always positive. So we do not need to put absolute values around this like we did with the critical value. If that is less than or equal to alpha, which we chose to be 5%, then I'm going to reject the null hypothesis. So the only difference between the critical value approach is on the critical value approach, I'm comparing this number, 1.65, to this number, 2, and saying, well, 2 is farther away from the null hypothesis than 1.65, which is like my cutoff point, so I reject the null hypothesis. Well, I could also, instead of comparing the numbers on the axis, the 1.65 and the 2, I could compare the areas under the curve. The area to the right of 1.65 is 5%. That's just alpha. The area to the right of my particular z statistic is called the p-value. And that's a probability too. That's the probability of landing at 2 or farther away. So if I find that my p-value is less than alpha, I can reject the null hypothesis. P-value, the opposite, p-value greater than alpha, I would accept the null hypothesis. So we should get the same answer whether we compare the numbers on the line or the areas under the curve. You should always get the same answer. I think the p-value approach is the one that's better and is more common because what the p-value tells you, this number, which we're going to look at in a second for this problem, actually tells you the probability that you're wrong by rejecting the null hypothesis. So let's take a look at the number. We know alpha is 0.05. So now we need to compare that to the p-value. Well, how can we find the area to the right of 2 in a z distribution? One way is to go to our z table right here, available in many places online, find the number 2, that's our z value, but this gives us the area to the left, So how do we get to the area to the right? So the area to the left is 0.9772. So 1 minus 0.9772 equals 0.0228. Yep, that is less than or equal to 0.05. So we reject the null hypothesis. Okay? So that's the only difference between the p-value approach and the critical value approach. And now when I say, okay, what does this mean in our research question? This means that we conclude Amazon stock returns are larger, greater than 5% per year, right? So that's what our conclusion statement could be. And then what's nice about the p-value approach is we could say there is a 2.28% chance that we are wrong in this conclusion. That's what's nice about the p-value approach. So I think the p-value approach is probably better because you can write that second sentence right here. And that's a valuable piece of information to have, right? Well, I know exactly the probability that I'm wrong using this data to come to this conclusion. Now let's take a look real quick at that green question, because remember last time we saw that in this case where we have a two-tailed hypothesis test because of the equal to and not equal to, we have to think a little bit differently about alpha. So in that case, when we go to our z distribution, calculating the z from our data centered at 0. Now we have to take our alpha, that 5%, and split it into both halves. 2.5%, 2.5%. So in this case, if two-tailed test, then the decision rule is p-value needs to be less than or equal to alpha divided by 2, or 2 times p-value needs to be less than or equal to alpha. Those are exactly the same statement, right? In either of these cases, reject null hypothesis. On the other hand, if we found that our p-value was greater than alpha over 2, or 2 times our p-value is greater than alpha, accept null hypothesis. All right? So we're going to look at this stuff in Excel in just a second, but just remember when you're doing a two-tailed test, that leads to confusion sometimes. You have to remember to split your alpha into both tails. So 5% is the alpha, but that 5% needs to be distributed into both sides because my rejection region has to have a total of 5% in it. And since I'm not saying whether I'm looking in the upper or lower tail in a two-tailed test, I need to take that and split it into both halves. And that's going to give me half of my alpha, or equivalently double my p-value. By the way, we looked at the table to get our p-value, but you should always use Excel to the extent possible. Equals norm dot dist. That function is going to give us probabilities in Excel. Remember, that function is just like going to the table. Norm.inv is also like going to the table. Direction For the distribution one, we put in a z-value, it gives us a probability. The inverse one, we put in a probability, it gives us a value. So we did that one to find the critical values last time. Also, if we're dealing with a world where we don't know the population standard deviation, we'd be using these functions. In the Excel example I'm about to do, we're going to be in this world. All right, so let me know if you have any questions about this stuff. You'll get plenty of practice in the book. And I'll see you guys in Excel in a second. Hey guys, here we are in Excel. So now we're going to actually implement a couple of those research questions, or actually just one of them, but two different versions from the notes that we just went over. But let's take a look first at the data that I've collected. So right here we have observation date, and I'm going to do since the beginning of 2013, has the unemployment rate been greater than 4.7%, the natural rate of unemployment? So you notice that I changed this a little bit from the question in the notes because I looked it up, and the Federal Reserve, 4.7% is currently what the Federal Reserve considers what's called the natural rate of unemployment. So I decided to go ahead. We might as well use the most up-to-date data if we can. So now we can ask this specific question that's from the real world. So I went and I collected unemployment rate data. It's monthly, as we can see. So this is January 1, 2013. At that time, the unemployment rate was 8%. We can see that we were kind of still coming out of the 2008 recession, 2007, 2008 recession. So we can see that the unemployment rate is kind of decreasing over time here. I've written the natural rate of unemployment here. You don't necessarily have to do that for a problem like this, but I wanted to show you something we can do that's kind of cool. So I'm going to click up here in this corner, and then I'm going to hit Command Shift or Control Shift if you're on a Windows machine, and then click over. That highlights all these rows for me. And then continuing to hold Control Shift or Command Shift, I hit down. This highlights all of my data for me. And then I just wanted to show you one thing we like to do as analysts or statisticians, or really anybody working with data. Oftentimes we can tell cool stories with charts. And once we start to get into the real world and are using data in business contexts, this is where we want to start using charts and presenting our data to clients and people that maybe don't understand statistics at the level that we do. So here we have unemployment rate versus natural. So unemployment rate versus natural rate. So that orange line is the natural rate of unemployment, which tells us here in the legend. And here we have the regular unemployment rate. I would probably want to go just thinking about like making nice charts. Unemployment rate. And then that'll update right there in the title. So just thinking about spelling and stuff like that. Spelling again and stuff like that. These are good things that we want to learn throughout the semester, although they're not a direct thing we're learning about in the class. Like for your project and project draft, that's later. Starting to think about the presentation of data, organization, and telling stories with charts is a good thing to think about. So what this chart tells us is, well, coming out of the 2008 recession, we had an unemployment rate that was above what the Federal Reserve considers the national rate. But then eventually we dip below it. And then what happens right here? We spike. This is coronavirus, right? So in March, before we really saw the impact, we saw a little bit of impact there. We bumped up from about 3.5% in February to 4.7% in March 2020. But then boom, that's where we get nailed by coronavirus. That is the April 2020 unemployment rate. And then you can see things have gotten a bit better since then as we've gotten out of lockdowns and stuff. But now we can ask, so we can see it kind of seems like on average the blue line is above the orange line. But remember, we don't know if that's a statistically significant difference, even if we find that that's true in the data. So we can always start out by thinking about these in the context of the story or research what we're trying to do, and always thinking about this is stuff that we want to probably present to clients in meaningful ways. So I just wanted you to get a chance to check that out and think about it. Now let's move on to our 2 research questions. So the first one, as I mentioned, is since the beginning, let's just zoom in a little bit here, we can see it better maybe. Since the beginning of 2013, has the unemployment rate been greater than 4.7%? So here I've defined mu, which we did in the notes. Mu in this case will represent the true population average unemployment rate. Now let's write down our hypotheses. So the null hypothesis, or let's write the alternative first, because it says if the answer to this is yes, then the alternative is true. Well, if the true average unemployment rate is greater than 4.7, then the answer to this question will be true, and we will accept the alternative hypothesis. On the other hand, if mu is less than or equal to 4.7, then the answer to this question will be no. So remember, some characteristics, our null always includes equality, which means that our alternative never includes equality, so that works here. 4.7 is going to be that cutoff point between our null and alternative hypothesis. Let's go with a 0.05 or 5% significance level. Remember, other common values are 0.1 for 10% and 0.01 for 1%. So then the first thing we want to do, remember, we generally want to decide that before we start making calculations. And the book will generally tell you what that will be, and I will generally tell you what that will be in Canvas quiz questions. And that's always up to the analyst what that number is going to be. Kind of like when we were doing confidence intervals. This is the significance level associated with a 95% confidence interval, by the way. But that's kind of thinking about two-tailed world down here, which we can discuss more in a second. So sample mean, we'll use the average function in Excel. So equals average, open parentheses. Now, the way I do these is I click on the first cell, just like when we made this chart a second ago. Then I do Command Shift or Control Shift if you're on Windows down. That highlights all of the data in that column. And so my average is 5.4. That's my sample average. Now clearly, 5.4 is greater than 4.7, but we cannot, so when we looked at the chart, our kind of intuition was correct. The blue line on average was higher than the orange line. But we do not yet have enough evidence to reject the null hypothesis and accept the alternative, because we don't know if that difference between 4.7 and 5.4 is statistically meaningful. Because as you know, even if the truth is that the unemployment rate is 4.7 on average, random variation could cause us to observe a sample unemployment rate that is above that average. So now we want to think about the likelihood of observing that 5.4 in a world where the truth is 4.7. So another thing we need, as you know, to make these calculations is the sample size. So I'll do equals count. That will count the observations in a set of cells. Go click on our unemployment rate, Control Shift or Command Shift down, enter. So we have 92 observations. Now we're going to do the sample standard deviation. The fact that we have not provided a population one implies that we're going to be doing a t statistic problem, right? Because we need to estimate the sample standard deviation. And anytime we're in that world, we need to use a t statistic. So here we go. Let's use stdev.s for sample. Go click on our first unemployment rate, Command Shift down arrow, enter. So there is my sample standard deviation. Now we're ready to get a t statistic. So to get a t statistic, we're going to take our null mean, our x bar, subtract our null mean, 4.7, and then divide by the standard error. So equals x bar minus 4.7, which is mu naught, the number that divides our alternative and null hypotheses, divided by, open parentheses, S, right here, divided by the square root of n. Because S divided by the square root of n is our standard error. So this whole part is dividing by the standard error. So that gives us a t statistic of 3.34. Okay? So real quick on the interpretation of what this means right here. So what we found up here is that our sample average is 0.7 units above our null mean, right? Because 5.4 minus 4.7 is 0.7. That is what percentage is the sample unemployment rate above the null mean? 0.7 percentage points. So we observed that it was higher, but we said, well, that's not enough to know if it's statistically higher. Well, now we've converted that 0.7, which notice that 0.7 is the numerator of this. This number right here, F7 minus 4.7, is that 0.7. We're taking that 0.7 and we're dividing it by the standard error. So we're converting that 0.7, which is an unemployment rate difference, to the language of statistics, which is standard errors. So now we can say the sample unemployment rate is 3.34 standard errors above the null mean. So that 0.7 unemployment rate number difference is the equivalent of 3.34 standard errors. So that's probably going to lead to rejecting the null, because that's pretty big. You can kind of start to see patterns in these. If you remember back in the last class, you had to think about how many observations, what percent of observations are within 1, 2, and 3 standard errors. Well, very few observations will be outside of 3. And we're about to find that when we look at our t critical value. So to get this, we're going to use equals t.inv, because right now we want to feed a probability or a significance level into a function, and it's going to spit out a degrees of freedom. Now we have to be a little bit careful here, because these functions always think about the probability to the left. But we're doing an upper tail test, so we're looking in the upper right tail. So if I'm looking for 5% in the upper tail, I'm looking for 0.95% in the lower or left tail. My degrees of freedom is n minus 1. And so my t critical value is 1.66. So I want to show you that Excel actually gives us a few other functions. So we could actually do equals t.inv dot, actually 2t, I thought it did rt here, but it doesn't. So sorry, we'll look at that in a second. But right now, so if we're doing the critical value approach, when we went over video 2.2, then all we do is we compare the absolute value of our t-stat to our t critical. Okay? Here we have that the absolute value of our t-stat. Where's that? That's 3.34. We don't have to flip it to positive, right? Because it's already positive. That is greater than t critical in this example. That means we should reject null hypothesis. And we'd say, yes, we have found enough evidence that we are willing to reject the null hypothesis that the true unemployment rate is less than or equal to 4.7 and accept the alternative hypothesis that the true average unemployment rate is greater than 4.7%. We do have enough evidence for that. We did not when we stopped here, but once we converted to the language of statistics, compared to the critical value that is based on our threshold, 5%, we find, yes, I am willing to reject the null hypothesis. The reason we're willing to do that is because the probability of observing this 5.4 is less than 5%. And we'll see that in a second. So now let's do the p-value approach. So now we need to figure out what's the probability associated with our t statistic. In that case, I'll use a t.dist function because this one, we feed it a critical value, 3.33, and then we give it a degrees of freedom, this -1. We always put true for cumulative in this class. There's going to be a problem with this one at first because that's way too big. That's because, remember, these always look in the right tail. Or sorry, these always look in the left tail to the left of the number. But we need to the right of the number. So let's do 1 minus to get that, 0.0061252. Now, to help you understand how these distribution works, there's other ways to write this. What happens if I get rid of 1 minus and put a negative in front of my t statistic? I get the same number again. Because now I'm looking to the left of the negative version of this number, which is the same value as to the right of the positive version. If you don't know why that is when I say that, go take a look at those bell curves again. They're centered at 0 and they're symmetric. So that's why this works. Okay? And this is where Excel actually provides, I believe, a right tail. Here's our number. Here's our degrees of freedom is n-1. Now this one, this .rt, now we're basically telling Excel, hey, look in the right tail instead of the left. Boom, we get the same number. So that's the same thing. Excel is basically doing the 1 minus for you when you do that. Okay? So now for the p-value approach, what did we do? Compare p-value and significance level. Now, this is a one-tailed test. So remember, for a two-tailed test, it's a little bit different than this because we're going to compare the alpha over 2 to the p-value. But for now, in a one-tailed test, we can just directly compare this p-value to our significance level. We find that the p-value is less than the significance level, okay? And that means reject the null hypothesis. So that means we should reject. You will always get the same answers in these, whether you use the critical or p-value approach. I think the p-value approach is better, which I'll explain right now, because with the p-value approach, you're going to have an easier time describing your results to somebody that doesn't know statistics. Because we can say the probability of observing a sample mean of 5.4 or more, if the true mean is 4.7, is 0.0006. It's at 0.0006. I'm not sure. I think I said 2 zeros accidentally the first time. But it's 0.0006. That is less than 5%, which is the threshold we set for ourselves before we looked at the data of whether we would reject the null. We got a lower probability of being wrong than we set for ourselves, and so we reject. You can think of significance level as you setting a threshold for yourself, saying, this is the maximum probability of being wrong about rejecting the null hypothesis that I will accept. We said, I will only reject the null hypothesis if there's a 5% chance of me being wrong or less. Well, we got less than 5%, so we reject the null hypothesis. Let's do the two-tailed version of this test real quick. So we change, if we got this question, since the beginning of 2013, has the unemployment rate been different than 4.7%? That's a different question because this is greater than, this is different than. Now we are talking about a two-tailed test. The null is that they are equal. The alternative is that they are not equal because we're not providing direction in the question the way we were up here. Alpha over 2 is going to equal this divided by 2. Why am I doing alpha divided by 2? Because I'm remembering that when I do a two-tailed test, I need to compare my p-value to alpha over 2. So now let's grab our t-statistic again. It's going to be the same value because our sample mean didn't change. Our sample size didn't change. Our sample standard deviation isn't going to change. None of that's changing, so I'll just click on this guy right here. T-statistic is the same. Now, however, if we do equals t dot inv, I have to be a little bit more careful. Remember up here, we put 0.95 in because it was okay for all of the 5% to be in the upper tail. But when we're doing a two-tail test, we have to think, well, I'm allowing 5% in both tails total. I'll divide it amongst them evenly, so there's only 2.5% in each tail. So if I want 2.5% in the upper tail, for example, that means there will be 97.5% to the left of the upper tail. Degrees of freedom is n minus 1 again. That doesn't change. And now we have a larger t-statistic. Notice that our threshold is farther away from 0. We need to get a bigger t-statistic, sorry, t-critical value. Our t-critical value is larger. Our threshold is larger in a two-tailed test because we're providing less information. We're saying, I don't know if it's bigger or smaller. So because I don't have as much information, I have to be harder on myself in terms of my threshold right here. So you got to move farther out to get that 2.5% in both tails, to break up your 5% into both tails. So now we still reject the null because our 3.34 is still bigger than the tree critical value. Notice that this test is still the same down here, and we still get the same result. But do note that imagine if our t-stat up here would have been 1.9. We calculated our t-stat and we got 1.9. We would have rejected in a one-tailed test, but we would have failed to reject the null hypothesis in a two-tailed test. So going from a one-tail to a two-tail could change your results. That is a possibility. It did not change them in this particular case. Let's take a look at our p-value. Our p-value is t.inv. The probability is 0.05, or sorry, the probability, we want a distribution, sorry, because we're figuring out a probability. X, 3.3, degrees of freedom, n minus 1, of course. True. This will give us the wrong one again because that's the too big of one, but we could do .rt, for example. Oops. Oh yeah, it doesn't want, when you do R2, it doesn't want the true in there. It just skipped that part. It just assumes you want it. So we got the same p-value again, but there's a couple ways to do it now. We already divided this by 2. So we could say p-value is less than alpha over 2. Reject. We could also say exactly the same thing. We could take this equals this times 2. That's another way to think about the p-value in a two-tailed test. And technically, oftentimes that's referred to the p-value in a two-tailed test. You actually double the one-tailed p-value to get the two-tailed p-value. But this is the exact same math. Now we could compare this to 5% because we, instead of dividing alpha by 2, multiplied our p-value by 2. That will always lead to the same result. So now we could say 2 p-value, or meaning 2 times p-value, is less than alpha, or significance. I called it significance level up here, but same thing, right? Alpha and significance level mean the same thing. And that also means reject. Okay? Now, I just want to point out, so that's it for these two problems. This is how you do those two problems. One thing I want to point out, though, is I did both of these. We had to use t, and that's because we had to, that's because we had to estimate the standard deviation right here. That means we need to use t, because this question is about a population mean, and we had to estimate the sample standard deviation. Okay? Now, if this was an example from the homework where they gave you a population standard deviation, well, first of all, you wouldn't have to make this calculation, right? Because they already told you what to use. So you wouldn't even have to make this calculation. They probably wouldn't even give you data. They would just tell you what the average is. And then you need to use z. Because if you're given the population standard deviation, you use a z distribution instead of a t distribution. Similarly, if you are ever doing a proportion problem, you may have to estimate the sample standard deviation by using p hat, but in any proportion problem, you always use a z distribution, not a t one. So the only time you actually use a t distribution is when you're doing a population mean problem and you have to estimate the sample standard deviation. Now, why do I usually do these? Because guess what happens to be the vast majority of the cases in the real world? We go collect data, we estimate a sample standard deviation. So although in this class it's only one of the cases, that one case ends up being the most common case in the real world. All right, so that's it. Make sure to let me know if you have any questions about these problems or this data, and I will talk to you guys soon. Okay, bye-bye.